Hello guys, so happy Tuesday. Today we will be exploring a simple pendulum system. Okay, our goal is to determine the relationship between period, frequency, and amplitude, specifically in a pendulum. Okay, so we talked about definition of what simple harmonic motion is. We know that's repeated or periodic back and forth motion about an equilibrium position. So a pendulum, right, is a simple harmonic oscillator. It oscillates, vibrates with a periodic pattern. Okay, so what you'll need today to do this lab, you need your calculator, you need your note card with your equations on it, and you need to open up a document in Google Classroom. Once you're in Classroom and you've opened up the document that appears on the right-hand side of the screen, you're going to click that link under Part 1, Procedure 1 to open up the Pendulum Lab. Okay, so a screen as shown on the left will pop up. You're going to click Intro. Once you click Intro, you will see a few ways in which you can manipulate the pendulum. You want to make sure that the length of the pendulum string, length 1, is set to 0.7 meters. You want the mass of the hanging mass to be 1 kilogram. Gravity, we want Earth's gravity, so our acceleration will be 9.8 meters per second squared. And friction, we're going to move our scale halfway between none and lots. Okay, we know if that we put no friction, then mechanical energy is conserved and the pendulum will continue to oscillate back and forth forever. If we put a lot of friction, the pendulum is going to come to rest a little bit sooner. Okay, which is not super accurate for a simple pendulum of this scale. So you want friction to be in between none and lots. On the bottom left-hand corner of the screen, we're going to need some tools here to help us determine the period, frequency, and amplitude. So we want to check stopwatch and period trace. What the stopwatch is going to allow us to do is to time how long it takes to make a vibration. Okay, we don't technically need the ruler, so you can uncheck that box if you'd like. The period trace will show us what an oscillation or vibration looks like on a pendulum. Okay, so just to show you what a period trace would look like, okay, it shows that as the pendulum moves from one amplitude through the equilibrium position to some maximum amplitude back to the equilibrium position would technically be an oscillation. We are going to measure an oscillation, also known as a full swing, as the time it takes the pendulum to move from its initial position to its final position, back to its initial position. So the time it takes to make one full swing. Okay, so I'm gonna release this and again show you what one full swing would look like. So start at an amplitude, okay, in this example I'm using 28 degrees, releasing the pendulum. 1, 2, 3, 4, 5 oscillations. So a trick here to make sure that our stopwatch begins exactly when our pendulum is released. On the bottom right-hand corner here, we're going to pause the simulation. So you're going to click pause on the simulation. You're going to click play on the stopwatch. That way, when I click play on the simulation, the stopwatch will begin exactly when the pendulum is released. On the top of the screen here, we see some dashed lines. What those dashed lines represent are degrees. Okay, so basically we have a protractor up here. When the pendulum is located at equilibrium, it states that the amplitude, the maximum displacement from equilibrium, in degrees in this case, is 0. As we move our pendulum further and further away from the equilibrium position, we see that that amplitude increases. Okay, for our first trial, we're going to set the amplitude to 15 degrees. Okay, so I take my mass, drag it back to 15 degrees. In order to determine the period, we're going to use the stopwatch to time 5 oscillations, so 5 full swings. We're going to record that time in data table 1. Okay, so let's give it a shot. I'm going to release. 1, 2, 3, 4, 5. Okay, so you're going to do the best that you can to stop it at the exact position in which you released it. The stopwatch will tell you how much time it takes for 5 swings. You'll record that in your data table. In order to find the period, right, the period is the time per oscillation. So you're going to take 8.47 seconds, divide by the number of oscillations, which in this case is 5, to determine the period. When we divide 8.47 seconds by 5 oscillations, we get 1.694 seconds. You're going to round the period to the first decimal place. So that would round to 1.7 seconds. So that means it takes 1.7 seconds for the pendulum to make 1 full swing, back and forth. To find the frequency, right, we know that frequency is the inverse. It's the number of oscillations per time. We can either take 8.47 seconds, or rather 5 swings, and divide by 8.47 seconds. Or we can use our relationship for frequency in terms of period and take the reciprocal. Okay, so our frequency, I'm just going to show the work over here. The frequency will be equal to 1 over 1.7 seconds which would give us 0.6 hertz. So in the last column, we would type that in, 0.6 hertz. Okay, so technically the exact value we would get would be 0.5882. We're going to, again, round to the first decimal place, 0.6 hertz. Okay, for our second trial, you're going to repeat that procedure. So if you click this little red button here, it'll reset your pendulum without changing any of your settings. You can click restart to restart your timer. For your second trial, you're going to displace the pendulum from 25 degrees, an amplitude of 25 degrees. And you will again release it, time how long it takes for 5 oscillations. Then you will calculate the period and the frequency. So in table 1, our independent variables, okay, that we're looking to determine would be the amplitude. So we're changing the amplitude. Amplitude is our independent variable. Our dependent variable would be the period. We're seeing how amplitude affects period in table 1. In part 2, we're investigating how the length of the string impacts the period and the frequency. So in data table 2, we want the mass of the system to remain the same. So mass here is going to be a controlled variable. The variable in which we're going to change is the length of the string. And you have the choice here to either increase or decrease the length of the string. So in the menu on the right-hand side where it says length 1, you can either increase or decrease the length of the string. I'm going to decrease it to 0.55 meters. Actually, let's make it an even 0.5. So I'm going to decrease the length to 0.5 meters. You want to keep that length consistent for those 2 trials. You'll again displace it first from 15 degrees, an amplitude of 15. Release it, time how long it takes for 5 swings, find the period and then the frequency. You'll then increase the amplitude again to 25 and repeat those same steps. Okay, you determine how length of the string affects the period or the frequency. Okay, in part 3, okay, in data table 3, what you're investigating is the impact of mass. So you want only the mass to vary. Mass is our independent variable. So the length you want to set back to 0.7 meters. You can increase or decrease the mass, up to you. I'm gonna decrease it to 0.7 kilograms. Once you've chosen a mass, you want that mass to stay consistent throughout these 2 trials. You will again displace it from 15 degrees, an amplitude of 15, find period and frequency. Displace it from 25 degrees, find period and frequency. In your analysis questions, please be sure to use data. Okay, so answering these 3 questions in particular, use data from table 1, table 2, or table 3 to justify your claim. So you'll state, for example, for number 1, does increasing the amplitude impact the period of the pendulum? If it impacts the period of pendulum, you would say, yes, increasing the amplitude impacts the period of the pendulum because you would use data from the table, specifically table 1, to prove your point. Okay, if amplitude doesn't affect the period, you would state the amplitude does not impact the period because when the amplitude is increased from 15 to 25 degrees, the period of the pendulum remains 0.1 seconds. Okay, so please use data from the tables to justify your claims. Okay, let me know if you have any questions and enjoy.